Hello everyone, this is Miss Nichols. This is a quick video sort of follow-up on the last couple of videos specifically focused on conservation of mass. The essential question for this video is what is mass and how do we measure it and track it in systems? So in physics, we're going to be using the symbol lowercase m to represent mass. And we're going to define mass as the total amount of stuff inside an object. So you may have learned that all objects are made up of atoms, and atoms are made up of electrons and protons and neutrons. So if you added up all of those things inside of an object, you would have its mass. It doesn't matter what the object looks like, it doesn't matter its shape or size or color. All that we care about is how much of those little tiny particles are inside. It's hard to tell because you can't obviously zoom in on something and see how much stuff it is. On Earth, we have something convenient called gravity that lets us detect how much mass something has by basically feeling how heavy it is. So for us, if you have a lot of mass, you're going to feel heavier, at least here on Earth. Typical units of mass are kilograms, pounds, and grams. We're going to try to use kilograms and grams as much as we can in this classroom because that's what the typical scientific community uses when we're talking about mass. 1 kilogram is approximately the same amount of mass as 1 pineapple. So if you ever held a pineapple, you can think of that as a kilogram. So if I ask you to estimate how many kilograms something is, picture a pineapple and try to figure out how many pineapples are inside that object. Grams, if you hear those, are smaller than kilograms. There are actually 1,000 grams in a kilogram, so 1,000 grams inside that pineapple. If you want to put it into fruit and vegetables, a gram is about the size of a pea, about the mass or the heaviness of a pea. Okay, so what kind of problems might we be solving with conservation of mass using closed systems? Well, you're going to want to start by creating your closed system and labeling that closed system at more than one time, because that's what we really want to see when we're talking about conservation of mass, is what does that mass look like over time when it's staying in the system. So for example, maybe one day ago, you have a pile of Legos in your room, and you have 200 Lego pieces. Each one has a mass of 2.5 grams, and you decide to make that into a closed system and keep all those Legos together in a pile, or in a box, if you wish. Because we're dealing with a closed system, it's really helpful to figure out what is the sigma mass for the system. What is the total amount of Legos, mass-wise, that we're going to have in this system? And so if you multiply 2 Legos by 2.5 grams a piece, you get a total mass of 500 grams of Legos in that system. Let's say you play with those Legos from yesterday to today, and now when you look at those Legos today, they look really different. You've got this wonderful series of structures and things that you've created out of Legos. In fact, you count that you have created 10 Lego structures, and you measure the mass of each one and discover that each one is 50 grams each. So for this new system, you can calculate the sigma mass again, 10 Lego structures at 50 grams a piece, and lo and behold, hopefully not surprising anybody, you discover that the sigma mass for this closed system is 500 grams because no Legos entered or left that system. As a reminder, sigma mass being the same shows that mass is being conserved from one day ago to today. So what would conservation of mass look like in an open system? Let's say we have an open system containing a cup with some froyo already in it. So somebody went to Sunny's down the corner and came back and gave us this cup, and we start off with froyo. Well, we don't like plain froyo, so we're going to add some stuff to the system. We're going to add, say, 20 grams worth of gummy bears to that system. And we're going to also add 30 grams of hot fudge. So those are my inputs, the things that are going into my system. Of course, wait a few more minutes, and we're going to start taking things out of the system as well. Let's say we take out 230 grams of assorted froyo gummy bear hot fudge sludgy deliciousness. So over the course of the day, the mass of this system has changed. We put things in, we took things out. Sigma is not going to stay the same, right? The cup and froyo will not have the same mass tomorrow as it did today. So we're not going to deal with sigma. Instead, we're going to talk about delta mass for this system. So you can calculate the overall delta mass, add the inputs, and take away the outputs. So positive 20 grams, add another 30 grams, that's the gummy bears and the hot fudge, and then subtract out the 230 grams that you ate, and you will end up with an overall delta mass of negative 180 grams for that system. So that cup lost 180 grams of mass somehow over the course of the day. Now, of course, hopefully this makes sense to you, that mass doesn't disappear from the universe. It actually moved from one system, which was the cup system, into another system, which was my body system, which means the mass of my body is going to increase by exactly 180 grams. But I'm in a different system, so that's a different problem for a different day. All right, we've reached the end of this video, so could you please take a minute to revisit the essential question? Make sure you now can tell me what is mass and how are we going to measure it and track it in the different kinds of systems, open versus closed, and what does that mean? Also have a great Calvin Hobbes for you today, where he appears to violate the conservation of mass and change one kind of mass into another or something of that nature. So enjoy. Thanks.